All right, hi everybody. So this is our last set of new material. It's labeled as week 14, but it's kind of both because we're landing in a weird place. But anyway, this is the last set of stuff for the semester. So hang on, we're almost there. Um, Two topics that we're going to talk about: systems of equations and matrices. We'll spend most of our time on this. And then talk about matrices. So we'll hold off on that and get to that later. But what I wanted to do here was let you know what a system of equations is and kind of get the big idea of what's happening, and then look at actually solving an example. So this is a system of equations. This is two equations written in two unknowns. So sometimes this is called a 2 by 2 system for two equations and two unknowns. Both equations here are linear. Notice nothing has an exponent other than 1 on it. So x plus 2y, 2x plus 3y. This is a linear, then, 2 by 2 system. We'll look at nonlinear stuff as well. But the thing that distinguishes a system of equations from a single equation is, think about like taking one of these just sort of by itself. We can move things around and rearrange this if we want. For example, I could solve it for y if I subtract x from both sides, and then divide by 2. So y is 1/2 times 5 minus x. I can move stuff around. I could solve for x a similar way. I can rearrange this in lots of different ways. But no matter what I do, I'm going to, the best I could do is get y in terms of x or x in terms of y. So there are infinitely many possibilities of x and y pairs that satisfy this equation. That means there's no, quote unquote solution to this. There are many solutions. For example, if x is 1 and y is 2, 1 plus 2 times 2 is 5. But similarly, x could be 5 and y could be 0, and then 5 plus 0 is also 5. So there's no unique solution to this because really what's happening is that this is describing a function, right? So to solve for two unknowns, we also need two or more. General idea is that if you've got two things you're solving for, you need at least two equations. We need another piece of information about them, basically, right? So that's where the system part comes in, is that we take these two equations together. The big curly brace, as usual, means this stuff all goes together. So we're talking about the same x and the same y here and looking for where these things sort of match up. Now, a system of two equations in two unknowns probably does, often does, have a solution. We'll look at cases where it doesn't in class, but the graphical interpretation of this, if I just graph these two things together, there's x plus 2y equals 5 in red, 2x plus 3y equals 5 in blue, and notice that they have this one shared point where they have the same xy coordinates at the same time. That's the solution to the system, -5, 5. Looking at the lines, that's going to be the only solution because everywhere else they're moving further apart, right? If we sort of move out from that point at -5, 5. So that's the solution. I can't get back to here we go. I'll just kind of make a note of that. Obviously, we're going to need to figure out, how we get there other than just typing it into Desmos. But that is the solution. Always good to know kind of where we're going. Okay, so we're going to look at two different ways to solve this, and for the sake of this video, I'll just do them both. We'll go over it again in class, but I think this is a thing that if you starts to click a little bit better the second time you see it, maybe. So one possibility would be to think of these two separate equations and look for ways that I could combine them, right? That's ultimately what we have to do is combine them together, but combine them together in a way that we get rid of something, right? That we figure out how to make it only be in terms of y or only in terms of x. So what we're going to do is called elimination. The way elimination works is you first decide what you're going to get rid of, right? So I might look at this and say, okay, there's x here, there's 2x here. If I take this whole first equation, so equation 1 and equation 2, just for the sake of, not having to write the whole thing again. If I take that whole first equation and multiply it by 2, what I get is 2x plus 4y equals 10. Right? Just multiply by 2 all the way across. And then I'm just going to copy the other equation, equation 2, down right under it. So I'm just carrying this down, 2x plus 3y equals 5, so that I have them kind of lined up with each other. Well, now notice that what I've done by scaling that first equation is made the coefficient on x match. So if I take these two equations now and subtract and combine like terms, what happens is they get 2x minus 2x, which is 0, and then 4y minus 3y. Those are like terms, again, the y terms. So 4 minus 3 would be just 1y, and then 10 minus 5. So y is 5. Now, in this case, we got just y by itself was 5, which is great. That tells me, the y coordinate of the solution. But the way I set this up in, again, trying to eliminate x and deciding, I'm going to multiply this by 2 so the coefficients match so that when I subtract, those go away. Whatever I got here would have been just in terms of y, which means I can solve for y then. If y is 5, then we do what's called back substitution, basically just back up. Sorry, I'm being neurotic about that k. Back substitution, basically just take that y value and plug it back in somewhere. It doesn't really matter where. So I'll just go with the first equation. X plus 2 in place of y, I'm going to put 5 equals 5. I've got a little weird. X plus 10. So x equals negative 5. And then our solution, these two things go together, would be this point, negative 5, 5. When x is negative 5, y is 5, that's that as an ordered pair. So the way elimination works is that you, and this part is something that you kind of figure out with experience, right? Where to look for things that kind of lend themselves to doing elimination, when to use elimination versus something else. Here, the thing I might see is that I've got 1x here and 2x's here. So if I multiply this one by 2, those match up. If I look at like the y terms here, 2y and 3y, I would have to take both of those and multiply up to 6, which means I have to manipulate both equations, which is, not like difficult, but it's a little more work. So that might be why I choose to eliminate x here. Again, we're going to have, options for how we do this. You never have to do one way or the other. Sometimes one might be a little more straightforward than the other. So another way to go about this is called substitution. To do substitution, we choose something here that we can solve for. So, for example, the thing that jumps out at me here is this. X plus 2y equals 5. If I take that first equation and subtract 2y from both sides, I get that x is 5 minus 2y. And if x is 5 minus 2y, then equation number 2 becomes 2 times 5 minus 2y. This is where we substitute, right? Plug in. Very important that you have to plug into the other equation though. The whole idea here is that one of these on its own is not sufficient. It doesn't give us enough information to solve the system. We need them both, which means, well, we need them both, right? I used equation 1, so now I need to use equation 2 as well. Here we combine them, right? We subtracted to combine them into one thing. So we're tying them both together here. The way we tie them together here is by solving in one and plugging into the other. Okay, so distribute, so 10 minus 4y plus 3y equals 5. So 10 minus y equals 5. I'm going to subtract 10 from both sides. Negative y equals negative 5. And then multiply or divide by negative 1. Right, the opposite of y is negative 5, so y itself is 5. And then again, I'm going to back substitute. So I'm just going to back up to earlier in the problem before I got rid of the other variable and plug that y value in anywhere that looks convenient, right? So y equals 5. All I want to do is figure out what x is to go with that. We could plug that in right here because we already did the work to get x by itself. Or I could plug it in right here, and that would give me the same thing. Or I could plug it in right here. They're all going to give you the same value for x, provided we didn't like make a mistake or something. So I'm going to plug into this thing right here. So x is 5 minus 2y, but I just figured out that y is 5. So 5 minus 10. So x is negative 5. And then again, our solution is the point, negative 5, 5. Okay, so things we need to figure out this week then. Of course, we need to like practice with the mechanics here and just make sure we have everything down. I know, it all sort of looks like a lot when you write it out like this, but keep in mind I did just do the problem twice side by side, right? So it's really like half this much work. So we need to figure out the mechanics and make sure we're comfortable with working through stuff. If you actually look at it, it's not really that bad. And then we also need to start working on, when to do what. One thing we'll talk about, we'll start with linear equations like this. For a linear 2x2 system, it kind of doesn't really matter that much. At the very worst, maybe you're going to have to do a little extra arithmetic to get it to work. So you see here, I've got a bunch of examples and that we'll be working on in class. In my instructions, I just said use either substitution or elimination, right? So like you're free to do either. And on any of these, you can do either. Sometimes one might be a little messier than another, but it's still going to work as long as we sort of run down all the details. We will get into, though, solving nonlinear equations as well. So for example, like this thing. This is a straight line, x minus y equals 3. But this, you got x squared and y squared terms. And the way that the substitution and elimination ideas work, elimination in particular, is that when you combine things by adding or subtracting, you're only going to combine like terms. These are not like terms. These are not like terms. That means there's not really any way I can do an elimination here, because if I try to add or subtract or whatever, these are not going to go together. They're not, nothing's going to drop out because these wouldn't combine, neither would these. That might be different, on a different problem. Like for here, for this one, I could eliminate x squared if I wanted to, because if I subtract these, x squared goes away, and then, I see what else happens. So for nonlinear stuff, we have to be a little more choosy, right? A little more careful about how we're combining things together. Our hand is kind of forced sometimes. And then we'll also get into solving larger systems, right? Like a 3 by 3, where again, we do the same stuff, we just do a little more of it. But again, it helps here if we can be kind of efficient with how we do things, right? Which would mean thinking about, when substitution works, when substitution works, maybe a little easier, right? Or it's a little more straightforward versus when that's true for elimination. So we'll have plenty of time in class to spend on working more problems. But for now, again, I wanted you to at least have seen this once, and you have, well, kind of twice really. Um, so I would sit with this a little bit. If you're feeling adventurous, maybe take this system and try to work through it again for yourself. Maybe try it a different way, right? I chose to eliminate X. You could choose to eliminate Y instead. Substitution, I chose to solve for this because solving for X is going to be the most straightforward version of that, right? Like I'm not going to have, if I solve for any of these other things, I'm going to end up needing to divide by 2 or divide by 3 or something like that, which might make things a little bit messier. But yeah, maybe give that a shot, try to work through it again on your own, and then we'll spend more time on this in class, of course. Okay, thanks. Hope y'all are having a good day, and I'll see you in class.